So, we just stopped at the point where we were trying to look for the interference pattern or the superposition of a plane wave and a spherical wave. So, here is the spherical wave, and this is the phase factor which comes due because it is a spherical wave, okay, and it is a Gaussian beam which is going through, and it can have a spherical wave of this kind. So, the spherical wave is, it is like a point source, and the wave front is concentric spheres growing and growing and growing, okay, and they have a radius of curvature which is given by Z0. So, let us get ahead. So, we want the interference between this and this, here you can see, and we will record it on this plate, and so E is ER plus E spherical, okay. So, this E becomes this e to the power I omega t minus k z E1, which is from here, the amplitude of the spherical wave, e to the power I k x square upon 2 z0 plus E0 e to the power I k x sin theta. So, that means this and this, I have just added it together, taken this part which is common part and out. So, now I must have E star E. E star E will be similar to a plane wave, the only new part is the spherical part. So, I will get a term which is E0 square, E1 square, and then E0 E1 term, and this whole term, okay, and this whole term. So, I have these two terms which both have this spherical phase factor here. This also has the spherical phase factor here, okay. All right. So, I get these two terms here, okay, and gamma characterizes the photographic material, and then after development the transmission factor of the plate is of this form as just like before, and the transmission is then given by this, okay. So, I have just put this here and put minus gamma by 2 on top, and did the same things which I have done for the plane wave, and finally, we came to a transmission, we come to a transmission factor which is here. So, the important part is everything is the same as before, but I have this a spherical the wave front, a spherical wave front here. That means, at the end of the transmission, I have to multiply it with the E reconstruction wave. Okay, so, this is the transmission, and this is exactly what is recorded on my plate. Okay. So, it looks as though the recording is such that it has encoded the spherical part of this wave front onto my hologram. Okay. So, when the hologram is illuminated by a plane wave, so I will illuminate it with a plane wave which is here. This is my hologram which I recorded in the previous slide, and this is my plane wave front which is coming through. Okay. So, E reconstruction is again just as before, E2 e to the power minus I omega t minus kz, and just as before, the amplitude of the reconstructing wave or reconstructing or illuminated by this plane wave need not be the same as what you did initially. Okay. So, the reconstructing wave need not be exactly the same as this, the amplitude can be different. Okay. So, that is indicated by this factor of E2 which is here. So, if I put in here, I have E2 and all this, I just open out and I get 1, 2, 3 terms like before. Now, the thing is, you just carefully look at this part, exponential minus I e to the power omega t minus kz minus kx sin theta plus kx square upon 2z0, while the other term has plus kx sin theta minus kx square upon 2z0. These two are like complex conjugates of each other. Okay. So, both these terms represents waves that are moving, of course, along the z direction, but because these two spherical terms come into the picture, they are spherical waves, they are no longer plane waves. They are spherical waves which are moving out this way. One is moving out this way and the other one is moving out this way. All right. So now let's just interpret these three terms. This light field consists of three waves. The first term represents a plane wave propagating in the same direction as the wave incident on the hologram, just like before. The second term represents a wave propagating at an angle theta to the z axis. Okay. So it is moving at an angle theta to the z axis, which is given by this term, sin theta. Okay. To the z axis, this is a spherical wave which is concave in the direction of propagation. Okay. So the plus and the minus sign, the sign of this makes a big difference. So it's definitely moving at an angle theta, this one, and this is also moving at an angle theta, but one is convex and one is concave. The third term represents a wave propagating at an angle theta to the z axis. This is also a spherical wave with a convex surface, this. Okay. This is like, this is like an expanding wave, while this is like a contracting wave. Okay. Image to a point at a position where the point was located during the hologram recording. So here I will get a image, it will come to a point, while this you will get a virtual image somewhere here. Okay. So that is what a point, so we started off with a point source, and that is what this is actually, wait. So what you get is something like this. The virtual image of a point source, this is a real image of a point source. So this is your hologram and this is your eye, and you are seeing this virtual image. And this is your real image of that point source, the point source which is giving out spherical wave fronts. Okay. So that is what I have tried to show in terms of wave fronts here. Okay. I don't know if the picture is good enough for your imagination. So I have this plane wave front, which is this is a hologram, it's reconstructing, and you are getting these two waves in this direction and in this direction at an angle theta to the z axis. And this gives you the virtual image here, because this is an expanding wave and this is actually focusing down to that one point here. So you are getting one image here and one image here. Okay, this is a virtual image. Okay, and this is called the real image. So this is for a point source. So this was, you have been able to understand little bit from the plane wavefront and the mathematical jugglery that was involved in it, how these waves travel and how they construct a hologram, and then how the image is reconstructed. Okay. So now let us see what happens if there is an object which is hologram of an arbitrary object. So I have just given the arbitrary object which looks something like this. This is my object. It's not a point source, it's not a plane wave, it's just something. Okay. So we have to find out the wave fronts that are emanating from this object. Okay. That wave front will definitely not be a plane wave front. though it may be illuminated by a plane wavefront, but what is coming out of this object after reflection from this, it will not be, it will definitely not be a plane wavefront. Okay. So, it will have some amount of phase factor involved in it. Okay. So, hologram of an arbitrary object, the wave arriving from the object to the photographic plate is of the form, is of this form, E spherical x y, okay, I have just put this x y, and E1 x y. So, you know, previously what I have taken is E1 as constant and then E0 as constant. But then now even that amplitude will have a certain variation, because it is kind of a object which is not a point source. Even in case of that point source, E1 was constant. I did not take E1 as a function of x and y. Okay. See here, E spherical, E1 I have just taken it as constant, more or less it is constant, only this phase is becoming larger and larger, phase fronts are becoming larger and larger. But now my object, in place of a small point source, I have a large object, and that itself, the amplitude itself will have a structure. It will not be constant all over, which you can see from this object here. Okay. It is not going to be constant. So, that is why I have to include a term which is E1 xy. The amplitude itself has a variation, and then of course, you have the wave itself, e to the power minus I omega t minus kz minus phi xy. I have written it like a general term of phi xy. In case of a point source, it was z square r square by 2 z0. You know, it was a well known a source, and one could define it very easily. Here the definition is by this function phi xy. Okay. So, the wavefront that is generated need not be spherical. It will be undulating, or it will not be a plane wavefront. It will have some kind of curvature, some kind of form, and that form is given by this phase, described by this phase, and it is going along the z axis, of course. Okay. So, it is a little bit more complicated situation than in case of a point source or a plane wavefront. So, the plane wavefront and the spherical wavefront was a way of understanding what actually happens, and here this is the actual object. Okay. So, how can we record it? Okay. We just pass in a ray of light. This is a mirror here. This is the object and that is the mirror. So, I have this ray of light here, or laser beam, of course, laser beam which is coming here, and this is a mirror, it gets reflected here. Okay. And then I have this ray of light also coming onto the object. Okay. And then the object becomes a secondary source. And that source is emitting some wave fronts. I have shown them almost like spherical, but they need not be exactly spherical. So, now I want the interference between these rays, this ray and these curved structures. Okay. So, I have a light, the reference is formed, the reference beam is formed by this reflected light, and the signal beam is also originating from that same light, but the secondary waves are formed here. and then I carry out this recording of the plate here. So, here I have written where E1 xy and phi xy are the amplitude and phase distributions, which you can understand, respectively from the light field. Field strengths recorded on the hologram is E star E as before. Take E star E of this. So, it will be of this form E0 square, E1 square. You just follow the same procedure as before, the same steps, same mathematical steps, and you get this. Only thing in this phase part, it is phi. We do not really know what exactly is phi. It can be only after we see the image, we will know what is this phi. Okay. So, it is some phi, some mathematical form which is which has a contribution in the x and the y direction. Okay. It is a function of x and y. Amplitude is also a function of x and y, and here we get this. Okay. Here I have not written that function of x and y, but actually E1 is a function of x and y. Okay. So, I have just given a general term, not the exact thing. So, when the now this part is recorded. Now, when the hologram is illuminated by a monochromatic wave, one can obtain the reconstructed wave. Okay. So, again I am illuminating it by a monochromatic wave. Okay. I just write monochromatic here because when you are illuminating the hologram, you need not have the same frequency as your reference or the signal wave. You've already done it. You've already done the recording with a reference wave and a signal wave. And now that you are reconstructing it, this wave, the recording part there, both the waves from the object and from the reference wave, they have to be coherent, no doubt, and that they have to be spatially coherent, temporally coherent. So, it is better that they come from the same light or having the same frequency. But when you are using a reference wave, you need not have the same frequency. It could be a different frequency from the original, because after all, what does it boil down to? It boils down to this diffraction pattern from the hologram made by this reconstructing wave. Okay. So, that is why I just write it should be a monochromatic wave, single free. But that lambda need not be the same as the ones you have used for your signal, spherical and reference wave. Okay. So, E out reconstruction, again we do the same thing, you multiply it by this transmission factor, which is of course dependent on this. So, you just use that, and reconstruction wave is a plane wave, and E out is E2 given by, so again it turns out to be 3 terms. Okay. 3 terms, just like before, it is you have 3 terms. This phase term I have just written as phi, and this sin theta is the direction in which it is going. Theta is giving the direction, phi is giving the phase, and then this part is the incident reconstructing wave which is going along here. Okay, so, you actually have these 2 and of course, this other one which is going here. So, what you are doing is, see, when you have this and you look back, I draw it with a dashed line because this is a virtual image, okay, and this is the real image. But most of the time in case of a holographic method, you are looking at the virtual image only. Remember, the eye, your eye is actually here, suppose your eye is here, and you are looking at the virtual image. It's like looking through a window at that image beyond, or looking at a mirror and then you can see that image. Now, what is the advantage of locking all these phase data into my hologram? You see that phase data is it does come into the picture here. In my output beam, you do have that phase that is coming out into the picture. Okay. And this phase is locked in this hologram. So, in real fact, what does it do? This phase things gives you a depth of that object. So, I do not know if you have seen any hologram, which white light holograms, you do get a lot of them. And what happens is, if you shift your eye from one end to the other, you will see a slightly different picture. Okay. You shift your eye onto the other side, you will see a slightly different picture. It is because of that factor that you are getting the idea of depth, and both your eyes are seeing a different part of the picture. Okay. So, here if your eye is here, if you just shift here and there, you will see a different part of this picture. So, you will get a lateral view. You move it this side, you move it that side, you will get some this part of the picture, this part of the picture you will get. So, that is the importance of, and then okay, you have a real part also. It is called a real image, but most of the time we are looking at this. This can also be checked out and it can be photographed without it can be photographed or projected onto a screen and like that. So, what have we done till now? So, what we have tried to show is this part only. Okay. Here. So, this is what we have shown a bit in detail. You have recorded and then you have seen the image, reconstructed the image. And the recording we have seen step by step we have followed. We have followed the for a plane wave and then for a spherical wave and then for a larger object which will give out a phase front which is not exactly spherical, but something like it. So, it gives you the concept of how a hologram is made and how you can reconstruct the image. And in the reconstruction, remember you get two images, one is virtual, one is called virtual and one is called real. Okay. Now, what we must do is, and this is the way you follow it. So, when we start off for recording, we should have a laser beam which is illuminating the object and is forming part of the reference beam. These two should have the same frequency. So, you will get a very fine interference pattern which is recorded. But when you reconstruct it, there is no need, actually there is just no need to have a laser beam, of course, no need to have one with the same frequency. Okay. So, you can imagine this hologram to be like striations you can have so many lines. Okay. So, there are so many lines per mm or however you record it. So, the better recording of this gives you a better picture of your original object. So, the more accurate your this recording is, the more you have more data of your actual object, the more real your image will look. Okay. So, the crux of the matter is how to record a very accurate hologram. That is what I had said in the previous slide, that when you have that silver halide and for a photographic plate, for a photographic plate you can just have this. They need not be very accurate, because you have to get finally a total picture. Okay. But in case of a holographic plate, it is very important to have, suppose your interference pattern is like this. Okay. And suppose your interference pattern is like this. Which one would you prefer? You would prefer these, something that is sharper, or even if it is this total thing should be recorded very well. Suppose you have a plate which is unable to record this curvature, You do not have enough silver halide or whatever in that. So, then your final picture will not imitate your object at all. The final picture will be some rough sketch of this. It will not be the exact replica of this. Okay. You can think of it as an illusion also, of course, because it is an image after all, virtual image. But it will not be the exact copy of this if you are unable to record these accurately. Whatever be the structure can be this or the structure can be this. Whichever be the structure, depending upon your object and kind of fine structure you have done. So, you can also have, say, very, very fine lines which are closer, but then because your silver halide is not good enough, some of these lines may be missed out. Once you miss out some of the lines, your data is also lost. Okay. So, in the next lecture, we will see how, what is so important about recording a good hologram.